Okay. Good afternoon, professors and students. Welcome to the tutorial lectures on the grand boundaries in material science. And in last section, Professor Srolovitz gave a very nice talk on the grand boundary energy, the grand boundary defects, and also the grand boundary metastability. And today, we will go together to the third part of the lecture on the grand boundary dynamics. So let's start it and give a big hand to Professor Srolovitz.
Thank you. Okay, so welcome back. It's nice to have an attentive class. So today what I'm going to do is go from the discussion of grain boundary structure, grain boundary thermodynamics, grain boundary metastability, and certain kinds of defects in grain boundaries. And what I'm going to do today is focus more on defects that affect how grain boundaries move, not just defects in the structure. I mean, of course, they're related. So for those of you who know me, my interest lately has been on this topic called disconnections. I'll tell you more about that. We'll talk a little bit, I'll remind you about the bicrystallography, which we talked about last time. I'll talk about the connection between disconnections and how grain boundaries move. And you'll see move has many meanings. I'll then talk about the migration, the formation of migration of disconnections, energy landscape for the motion, grain boundary shear coupling, grain boundary mobility. And then I'm going to start getting into the lecture topic for next time, which is grain boundaries and microstructures. And what you'll see, at least for today's talk, is a focus on how things that exist in the microstructure affect and change the way grain boundaries themselves move. So that's constraint effects. Okay, so I will first do a very quick review. For those of you who fell asleep last time, no, just kidding. So we'll start with a simple grain boundary. This is a sigma 5 grain boundary in a simple cubic, well, actually simple square lattice. And it's a symmetric grain boundary. It's a sigma 5. You can see the two crystals are misoriented by the same amount from the axis. So that grain boundary, the blue line, is a mirror in this case. And then what we do, as you recall from last time, is you extend the black lattice down and the white lattice up so they fill space. And you see that gives you a periodicity again, which I show in red when you interpenetrate the two lattices. And that periodic lattice there is the lattice that's appropriate for talking about a bicrystal. So we call that the coincident site lattice. We spoke about that last time. So just remind you of what it looks like. And what you see here is if you take the black lattice and translate it to, the right, get my directions right, by that Burger's vector in B, the same lattice is reproduced, but it's translated by some amount. So a very small displacement of magnitude B can give you a large change in the origin of the coincident site lattice. And if I repeat that for all possible shifts that keep that lattice invariant, I generate, so I look at all the possible translation vectors that bring any black atom in contact with any white atom. If I look at all possible translations, I end up with this very fine lattice, which corresponds to what you get if you shift the whole black lattice down by that amount, or up by that amount, or over by that amount, etc. If I do all of those, I get this very fine lattice, and we call that the DSC lattice, which is the displacement shift complete lattice, or it's the displacements which are symmetry conserving. And that's basically the picture. So the important thing to remember from this is that given any lattice and any misorientation between the crystals, I can define a coincident site lattice and a DSC lattice. And once I have those, translation vectors in the DSC lattice are basically the fundamental translation vectors associated with the grain boundary. And those will be the important vectors when we talk about grain boundary defects. Just like in a perfect crystal, if I do a translation by a lattice vector or any lattice translation vector, then I can say that's a legitimate Burgers vector for a dislocation. We're going to do the same thing here. Okay? So that's all a reminder. Okay? Okay, so let me start here by talking about defects, and let me start by talking about dislocations. And I want to create a dislocation. I'm going to introduce the symmetry ideas to create a dislocation, but I'm going to do it in a language which makes it easy to go and now talk about grain boundaries next. Okay? So what we're going to do is we have a single crystal shown here, and what I'm going to do is I'm going to say I have a slip plane which I draw in blue there. And all the atoms below there I'll color white, and all the atoms above there I'll color black. So this is like a grain boundary where the misorientation angle is 0 degrees. Okay, which is another way of saying the perfect crystal, right? Okay, now what I'm going to do is highlight all these atoms here in yellow. So again, I've extended the black atoms down, the white atoms up, and I end up with all these gray atoms. And what I'm going to do is I'm going to just color some region here yellow. And then what I'm going to do is in that yellow region, I'm going to translate this crystal, all those atoms here, all the black atoms here, to the right according to a translation vector of this lattice, shown as the B there. Okay? And if I do that, I can go to here, and if I throw out all the black atoms below this line and all the white atoms above that line, I end up with this. And so all I've done is I've produced a perfect edge dislocation. So if you like to think about dislocations in the Volterra sense, what we would have done is we would have just cut along this line, translated over just this part, and then connected it back up, and that would be the Volterra process for creating a dislocation. Okay, so if I look at that, if I do a loop around it, I do a Burgers circuit, I go all the way around it, counting how many steps I take in each direction, and I have a closure failure here, B, and this B is the translation vector of the original lattice, and this B is the strength of the dislocation, or the Burgers vector. So more mathematically, what you do is you say the Burgers vector is defined as the integral around any path of the displacement vector integrated all the way around the path. So that's the classic definition of a Burgers vector dislocation. So that's a Burgers circuit. Okay? So again, the process, I take the black lattice, send it down, the white lattice, extend it up, I displace over half of it, I throw out all the atoms below that line, the blue line, and all the white atoms above that line, and redraw it, and I get a dislocation. Okay? So now I want to do the same thing, exactly the same process in a grain boundary. Okay? We're going to do exactly the same thing. The only difference is the lattice we're talking about now is this dichromatic pattern, this black and white lattice that I had before.
It's a pointer.
Ah, yes, thank you. I always forget to use the pointer.
The other one?
Okay, so I'm going to apply this now to a grain boundary. So, the picture you saw before, it's the black and white lattice where the gray atoms make up the coincident site lattice. The little black lines here are the DSC lattice. This is going to be my grain boundary plane. And so now I'm going to displace all the black atoms to the right by that translation vector of the DSC lattice. That's shown here. But I'm only going to do it in the yellow region. So I translate them all to the right. And as you saw before, when I do a translation by a DSC lattice, it shifts the origin of the CSL. And so I have that. And you can see now there's a step. And so what I'm going to do now is throw out the black atoms below the line, the white atoms above the line. And I end up with this. So again, I have my grain boundary that I had before. But now when all I did is that translation, that slip along half the slip plane, which here is the grain boundary, when I do that sliding by one translation vector here, you can see if I go around, I still have a Burger's circuit, where the Burger's circuit tells me there's a closure failure. So I've got a Burger's vector. So this defect, just like the dislocation, has a non-zero Burger's vector. But you can see that this plane of atoms here, this plane here where the atoms are coincident, I've also introduced a step, okay? And so this kind of defect is not a dislocation. We call it a disconnection. And a disconnection is a defect that can only exist in the bicrystal, so therefore only in the grain boundary. And it's characterized by both a Burger's vector, which must be a translation vector of the DSC lattice, plus a step, and this step will also be a translation vector of the DSC lattice. So again, the difference between a disconnection and a dislocation is the disconnection may have a step in addition to the Burger's vector. Okay? Good? Good? Yes, question?
Does the step size correspond to the shift in the origin when you do this, when you do the sliding of this DSL?
Yeah, so if I tell you how I'm going to shift it over, you can figure out what the step height must be. And I will show you actually on my next slide. Yes, and you'll see that exactly the next slide. So one thing I'll just point out here is, you see, I said, well, I threw out all the atoms below, all the black atoms below these coincident sites. But I could have chosen this one, just thrown out all the black atoms there. Or I could have chosen that one and thrown out all the black atoms below that. So in fact, as Professor Chen just noted, there's not just one step associated with this Burger's vector. There's a series of possible steps, and it's just a regular series. And so if I know how big the smallest one is, I can figure out all the other ones because they are one CSL spacing apart. Okay? So for each Burger's vector, there is an infinite set of possible heights that may exist. I'm not saying which ones do exist, but they're in practice, but all of those are possibilities. And it's just like if I take an FCC crystal. I can take a Burger's vector to be along a 1/2 110, but I can also choose a translation vector, a Burger's vector, to be 100 or 200 or pick 1 2 3. They're all translation vectors which the crystallography allows, but energies are going to determine which ones actually are important. It's usually the low energy ones that matter. So all that the crystallography and these defects require is that it is a translation vector of the crystal. Okay? So that's just what crystallography allows. Okay? That's exactly what Professor Chen was trying to say when I interrupted him.
So this part depends on confusion. When you throw the atoms away, actually, you simply suggest that you can remove some atom with the added defects.
No, I don't actually have to remove the atoms. As I show you, there's a conservative kinds of formation process and a non-conservative ones. So as long as I put in a positive and negative one together, it's conservative. And if the Berger's vector is parallel to the boundary plane, its motion will be conservative as well. Okay? Okay, so again, if I throw out the black atoms above and below that line, I can, if I throw out all the black atoms below here and the white atoms above there, I have the picture on the left. If I throw out all the black atoms down here below the white atoms above that line, then I have the picture on the right. If I do a Berger circuit, you find out they have exactly the same Berger's vector, but this height, step height, is of size 1 DSC lattice parameter, positive, and this one's 1, 2, 4 DSC vectors, lattice parameters, in the opposite sign. Okay? So, if I'm going to describe this disconnection for you, I have to tell you two things. If it was a dislocation, I would just tell you the Berger's vector, and that's all you need to know. On the other hand, here I have to tell you both the Berger's vector and the step height. Step height can be positive or negative, and there is a particular step height. So both of those things are characteristics of the disconnection in the same sense that the Berger's vector alone is a characterization of a dislocation in a crystal. Okay? Good? Now, let's look at a particular disconnection where I'm going to pick one that happens to have a Berger's vector of 0 and a step height of 5/2, and these are in units of the DSC lattice vector, lattice parameter. And so this is an atomistic simulation, just colored all the atoms according to their potential energy. And now if I go in and look at the stress, so if this is the y direction, that's the x direction, then the stress field of here are these two little steps. First I'll point out, first it's stepping down and then stepping back up. Very small, okay? And if I look at it, you can see that there's a little bit of stress. It's very small, and it's very localized around the core of the disconnection. On the other hand, if I take a disconnection that has a Berger's vector of 1, these are two different step heights, 3/2 and 4, if I look at the stress field, now it's much longer ranged, and even though these have two different step heights, the Berger's vector is the same and the stress field is the same because the elastic field is determined by the Berger's vector, not by the step height. The step height can only change things sort of in the core region. It has to do with very localized bonding, okay? But no long-range elastic field. These, with 1 here, these are just regular plain old stress fields of dislocations. So this is just the stress field of an edge dislocation. Keep in mind, the material is anisotropic, and so when you tilt it up and down, it's not quite symmetric left and right because the material is anisotropic. Okay?
But even the stress is the same. Would the grain boundary energy be different?
Yes, the grain boundary energy will be different, and I will talk about that on the next slide. I mean, the point is they are different defects. Defects have an energy, and that energy depends on B and H, both. The elastic part of the energy only depends on B. Okay. So the experts will recognize this as a grain boundary with a disconnection pair. Like, what else could it be? Right? Okay, so we start with a flat grain boundary, and we introduce something that has, it steps up here and steps down here. The Burger's vectors have opposite sense. The step has opposite sense, minus h plus h. And these are separated by some distance delta. Okay? So what I'm going to talk about now is how much energy does it cost to put a disconnection dipole or a pair into the grain boundary. So I'm not telling you what the energy of the grain boundary is. I'm telling you how much extra it is when I put in that disconnection pair. Okay? So that energy has three parts. The first part is a step energy, and it's proportional. So, by the way, so this keeps going out in this direction here, right? So this grain boundary is now longer, or has a larger area than when it was flat. So the grain boundary length, the grain boundary area is larger, so it's larger by an amount that's proportional to the step height h. And it depends on what this grain boundary energy per unit area is of that part, which is the step. So imagine this is a macroscopic step. This would be the energy, the grain boundary energy of that facet. Okay? So it's proportional to the step height. And there's two of them because I step up and I step down. Now, the next part is these things are dislocations. Then dislocations have two things. They have an energy associated with the core of the dislocation, plus they have a long-range elastic energy, a long-range elastic field. So the energy associated with core, I could call this either a constant value, E core. You know, if you go back to like the theory of dislocation, like Hirth and Lodo, they'll tell you it goes like proportional to Burger's vector square. Don't take that too seriously. Okay. How do I get it? I can only get this from some kind of atomistic simulation. You know, it depends on local bonding and local core structure. Okay? And since there are two disconnections, there are two cores, hence the two in the front. Zeta, I think the technical word for that is, it's a fudge factor. That is a constant we put in there that we have no idea how big it is, unless we do a simulation. And then we have the long-range elasticity. That is, I can think about the long-range elasticity in the following way. If I put these two disconnections together such that, you know, the boundary is flat, and I can say how much energy does it take to separate them to some distance delta. That's mechanical work. And that goes like the logarithm of the separation. This is the core size. This is a constant, which looks like the shear modulus divided by 4 pi 1 minus nu. This happened to be an edge. If it's a screw, then you don't have the 1 minus nu floating around. And it's proportional to the square of the Burger's vector, because as we know, two dislocations plus and minus interacting with each other have an energy that goes like Burger's vector squared. Okay? So those are all the pieces. Now, if I want to know what the total energy of the grain boundary is, it's just the energy I had before I put in the disconnection plus this. Okay? Because that's the energy it cost me to introduce that. Okay, good? Okay, now, you could say, well, this is 2 dimensions. You know, theorists always play these games, do it in 2 dimensions instead of 3 dimensions. You can, oops, sorry. I can be a little bit more sophisticated about it, and I can put it in and put kinks on the disconnections like this, the kinks on the steps, or like that, or I can say it nucleates on a flat surface in 3 dimensions, like a little pillbox. You can be as sophisticated as you want. I don't really do that here, partly because it just makes it complicated. And trying to get the ideas across. Okay. If you're interested, you can look at our review paper on the subject. Okay, so again, the experts will recognize this is a grain boundary between 2 crystals, and this is just the cross section of this with a disconnection pair. Okay? Now, let me imagine that I have put a disconnection through there, and I shear it over by a Burgers vector. And if I put on an applied stress like this, shear like this, and the Burgers vector is in this direction, when it goes through, I'm doing mechanical work. So this is the disconnection version of the Peach-Kohler force times how far it moves. So it's force times distance. Okay? You've all seen this before. Okay, and notice how much it shears over when I put on that stress. Well, the stress couples to the Burgers vector, and the distance at which it slides is just related to the Burgers vector. It couldn't care less what h is. Okay? So this is how I can get grain boundary sliding, by propagating something where there's 0 step height h. Okay, now, let me do something a little bit more thermodynamic. Oops, sorry. What's going on here? Okay, sorry. Let's imagine that I have a bicrystal, and the chemical potential in the top half is different than the chemical potential in the bottom grain. So what could that be? It could be strain energy differences between the top and the bottom. It could be, for example, it could be if the grain boundary was curved, then there's the curvature energy, which is the grain boundary energy times the mean curvature. Or if this material had a dipole moment and I applied, say, an electric field, and this one, the dipole moment is pointing up, and this one is pointing that way, then it would be the dipole moment times the field H or B or E or whatever you call it. Okay? So if the 2 materials have different chemical potentials on the 2 sides, then that also wants to make the grain boundary move from the region where the chemical potential is high to the region where it's low. And the chemical potential difference, the work done to move the grain boundary from here up to there, just depends on how much more of this blue crystal I've created when it moves up, and how much of the yellow crystal I've removed. So if I remove the high energy part and put in low energy part, that means the energy goes down when the grain boundary moves up. Okay? Well, so it depends, it's proportional to how far it moves up, how far the disconnections have moved sideways, so times the step height, the difference in chemical potential. If we do this the way a mechanician would do it, say it's just the jump in the chemical potential across the grain boundary, and we just call that jump psi. So this means the jump in chemical potential when you cross the boundary. Okay? So if I say there's a jump in chemical potential when you cross the boundary, then just like the stress will move the grain boundary by coupling the Burgers vector, a difference in chemical potential when will couple to the disconnections by connecting to the step height h. Okay? So psi couples to h and stress couples to Berger's vector. It's not surprising, right? Okay? Okay. Boop, 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 boop. So, disconnections with non-zero Berger's vector and with non-zero step heights suggest that when the disconnections move, the grain boundary should both translate and shear simultaneously. And so if I tell you what B and H are, I know what the ratio is between how much it shears and how much it migrates. And we call that shear coupling, that ratio, and I'll go through that in a minute. Okay, before I do it though, I want to remind you that the grain boundary energy here, or the formation energy for the disconnections, depends both on H and B. And just to remind you that any grain boundary has a specific set of allowed values of H and B. If I change the misorientation, I will change the H's and B's that are allowed. Okay? So if I look at different grain boundaries, the H and B's which are permissible are different. And that's what's shown here. If I pick a particular misorientation corresponding in this case to sigma 5, corresponding to sigma 5 here, and I look at all the possible combinations of H and B I can have, I have a set of formation energies. Okay? And that set is just determined by the crystallography, which B's, which H's I'm allowed. If I go to another grain boundary, in this case a sigma 13, I have a different set. If I go to cases corresponding to sigma 37, I have another set. So the formation energies of different disconnections are different, and each grain boundary has its own spectrum of allowed energies. Okay? So the spectrum is quantized, and it depends on the misorientation between the grains. Okay? Now, if you tell me which misorientation it has, a bicrystal has, I will tell you what B's and H's are allowed. You plug it into the formulas, and I get these spectra. We know how to do every part of that. Okay? So I can always characterize this spectrum. Okay? So let me go back to this formula that I had here. And let me now look at the energy as a function of separation delta. Okay, and that's shown here. So the formation energy that I told you had a step part, a core part, and an elastic interaction part like that. And so those are these three terms here. And that energy just goes up with separation. And the reason it's going up with separation is there's a long-range elastic interaction. You know, if I ask you the question, what is the equilibrium concentration of dislocations in the material? The answer is always 0. And it's 0 because whatever I put them in, they just want to collapse back. Unless I apply a stress or I apply a chemical potential difference. So as I showed you before, the stress couples to the Berger's vector and couples to that delta. So that's a blue line here. Or if I apply a chemical potential jump, psi, and I have a step height h, and that's the separation delta. So these two things together give me this linear curve, linear in delta, the separation. Okay? They both do the same thing. And so now if I add the red curve to the blue curve, I get the green curve. Now, this is exactly the way we do this. This is exactly the way we do nucleation theory, right? You know, there's an energy difference between two phases. There's a surface energy. You bounce them out, and when it gets big enough, it lowers the energy for it to continue to grow. Here, if I apply a stress or apply a chemical potential difference, assuming I can get across the barrier, then the energy will go down if those two things separate. Okay? So there is a critical size given by the place where that curve has zero slope, and there's an energy which is the formation energy of the critical size. Okay? Just like nucleation theory. Okay? So we all know how to do that. Right?
Applies to the thermal scenario.
Yes, this is athermal. So there are many ways to cross the barrier. I'm just telling you what the barrier is. I haven't told you how to cross it yet. But it's a good question. Hold that thought. We will do the statistical mechanics. Okay. So the critical size goes down when you increase the stress. It goes down when you increase the chemical potential jump. Just like that. The other thing I'll note is while this looks like homogeneous nucleation theory, in most cases in practice, nucleation happens heterogeneously. So as we all know, if I look at a solid crystallite trying to nucleate in a liquid, I can calculate the energy to form a sphere. But if it's heterogeneous and the crystal grows on a surface, then the formation energy is much lower. But it's still proportional to exactly the same thing. Just depends on that wetting angle in the nucleation case. Same thing here. So even though the may not actually happen homogeneously, the homogeneous part tells me the scaling. So I'll just also mention there's one more barrier in the problem I haven't talked about yet, and that is just like when I try to move a dislocation through a material, even after I form it, there's a Peierls barrier. There's effectively a Peierls barrier or a migration barrier for disconnections as well. And we will calculate that. Okay? So, first, let me start with a simple grain boundary, a sigma 941 grain boundary. Now, a sigma 941 grain boundary is just a sigma 5 boundary with these small additional units which are spaced far apart, which we call before the minority units in the grain boundary structure, or we can also call these secondary grain boundary dislocations. Depends on what language you grew up with. Okay, either way. Okay. The point is, even though it's not such a simple boundary, it's a sigma 941 on a 0, 10, 29 plane. Right? Probably would have been your first choice, right? But I pick it because it is complicated. Now, I can put a disconnection pair on here. So if you look, this actually is a step down. Here it's a step up. You still see the secondary grain boundary dislocations here. Well, they kind of get lost a little bit. But you put the disconnections on whatever the structure of that grain boundary is. So even though it's sigma 941, it's really sigma 5 plus some mess on it. Periodic mess, right? By the way, I keep saying this because everybody always asks. If it's not a sigma boundary, it's exactly like the one I drew you, except the secondary grain boundary dislocations are not periodic, they're aperiodic. Okay? Okay, so for this particular material, the DSC lattice parameter is this, so this is aluminum. So DSC lattice parameter is just the lattice parameter of the cubic unit cell divided by the square root of 10. That's the lattice parameter. And then the simplest combination of B and H is where this is magnitude 1. And say it's magnitude minus 1. So that's this pair. So if this is 1 minus 1, this is minus 1, 1. The other way around. Okay? It's a pair. Now, with a complicated structure like this, don't these things with these really, really tiny Burgers vectors, these really, really tiny step heights, how could that possibly matter given how complicated this boundary is to begin with? Well, if I look at the stress field associated with this material, with this grain boundary, you have this very fine scale stress. This very fine scale stress associated with the details of the sigma 5 cores and the secondary grain boundary dislocations. But the disconnections, they're just like standing out there in the open, right? They have a long range elastic field, which is very clear. And they're opposite because one's a plus disconnection, one's a minus disconnection. Okay? So even a complicated grain boundary with a very small Burgers vector still has a long-range elastic field that will couple with an applied stress. Now, there's a small step height here, very small, but it's still there. Again, it's the same magnitude as this. Okay, now, let me stick with the sigma 941 grain boundary, just because I can do it, so I'll be perverse and stick with this one. And let me ask, what is the actual energy as a function of separation of these two disconnections? Right? I wrote down a very simple model for it, but does it really work? So what we can do is an atomistic simulation. We call this nudged elastic band calculation. Doesn't matter for this discussion. But if I look at the energy of this material, of this grain boundary, as a function of separation of the disconnections, I have this red curve, and superimposed on that, I have this black curve. So this black curve is the actual energy as a function of separation. The height here, that's the Peierls barrier for the disconnection. The red curve here, this is telling me what the nucleation barrier is, the formation barrier is, the way I did it before. So if I go back and get rid of all the black part and just make a curve or long bottoms here, the center of all these bottoms, that's what I have. And that agrees very well with the very simplistic calculation I did before. Okay, so that would be a barrier height. Okay, I can tell you more about this later if people have questions, but so that's the idea. Okay, so the point is everything is here we can calculate. So I know how much the energy is, I know what the energy to separate is, and now I can start addressing the question of how easy is it to form these and how easy is it to move these. And I care about that because the way the grain boundary is going to move depend on the ease with which I form and move these. Okay? But now I understand the thermodynamics and I understand the barrier, so I understand the energy or the stresses or the thermal fluctuations I need to get this. Okay? So we've done the thermodynamics. Now we have to do the statistical mechanics. Okay?
David, but the stress field of the grain boundary dislocation extent
Yes.
depends on their periodicity, right? Once they are very close, separated,
Yeah.
I think the stress field will be much narrower.
Well, so you see right down here when the separation is very small, it drops very fast. So that's that part that you were just worried about. Okay?
This is smaller one.
I keep switching them. Okay, now, up to now, I've talked all about the misorientation. We talked about Berger's vector and step heights, right? But that comes from the DSC lattice, and that only depends on the misorientation. Okay? Now, if the Berger's vector, let's say, this is a grain boundary, as you can obviously tell. If the Berger's vector is parallel to this line, to the grain boundary, then the disconnection can just glide along this, just like a dislocation slip plane. Okay? No problem. On the other hand, if I take that same disconnection and I change the orientation of the boundary like this, the only way it can move along is by adding matter or removing matter, and that's a non-conservative motion. So I would need some diffusion for that. So we have the concept just like we have for dislocations. We've got glide and we've got climb. Okay? Now let's go back here and imagine I have a grain boundary that's inclined by an angle phi here. If it's inclined by an angle phi, that means the shape I can represent like this, and that's my approximation to the straight line. Well, in atomic systems, there are no continuous curves anyway. But you can see then that when I change the inclination, I'm necessarily putting in a specific constant density of disconnections. And if I tell you what the angle it is compared to the symmetric orientation, then that angle is related to the step height and the spacing between them, d. Okay? Now, let's actually look at an example. So this is a sigma 29 grain misorientation of 46 degrees about a 100 axis. Okay? So this is the DSC lattice associated with that. Those are all the black and white atoms. It's sigma 29. So 1 out of 29 atoms is in coincidence in the plane. And now I could create boundaries with any inclination I want, because if I draw a blue line here, throw out all the black atoms here and all the white atoms above here, then I have a grain boundary, which is sigma 29 with this misorientation, this inclination. And if I know that, I can look to see which disconnections can glide along this boundary. Well, it'll be the ones that correspond to a translation vector like that. So it turns out for this one, the Berger's vector and the step height is, if this is a DSC, those are the ones that are going to be important. And if I do this inclination, these are the ones that overlap, and they look like that. Okay? So crystal misorientation determines what the DSC is, but it's the inclination that tells me which of these things are going to be important for moving, because it's going to be the ones that can move conservatively that'll be most important. Okay? So different depending on inclination. So inclination tells me which sets can move conservatively. Okay, so how is this related to actually grain boundaries moving? So some of you have seen this before. This is a movie from Marc Legros' group in France. I actually love this movie. So first, before I turn it on, this is a grain boundary here. The film has some thickness in this direction. So this is like the bottom and the top surface of your TEM foil. And there's another grain boundary and another one. So this is basically a triple junction. So this is a nanocrystalline material, ultra fine grain, well maybe not nano, but ultra fine grain. And what they do is they let the grain growth happen until the grain boundaries stop moving. And then he applies a stress, in this case in this direction. Sorry, the reproduction's not great, but it's still a beautiful movie. So he's applying the stress. Is that moving? Oh, come on. Now you see this boundary is moving down, but if you look along the grain boundary, there's something that's moving along laterally along the grain boundary. That's what we're talking about. Those are the disconnections. And you can watch the disconnections move along the grain boundary as those grain boundaries migrate. If you keep watching here, something interesting happens. So you can see them all moving along here in that direction. If you keep watching, if you keep watching, come on, you eventually start to see disconnections going the other direction. Oh, maybe not in this movie. Because, you know, the point is the grain boundary can keep moving this way, but if I have disconnections that have the opposite sign, they can still translate the same boundary, but just by moving in the opposite direction. And so you can have both kinds of motion. I thought I had one where it shows them both moving. Okay, so many observations like this. And you say, well, this, yeah.
What's the motion speed?
This is when this is 32 frames per second.
I don't know.
I think it should be pretty fast.
Yeah. Sorry, I don't know. So all this has been really been a lot of interest since the early 2000s, but in fact, this is really a very old observation that when you apply a stress, you can drive grain motion. And I plug in, this is from a really, really old paper from 1953. It's known as the Parker-Washburn experiment. And what they do is really interesting. They just have a macroscopic bicrystal. They're looking at it from an optical microscope. And what they're doing is they're looking down here, they're looking at the reflection of the light from here. And they're going to put on a load here, and when they put on the load, the grain boundary moves. So here's some pictures from the 1953 paper, all optical microscopy. So the grain boundary starts here, they're pushing like that, and you can see the grain boundary moves over, then from here moves over some more. When they do that, now the interesting thing is now, if I start at this point, show dots here, and I push the load the other way, I pull up instead of push down, the grain boundary moves in the opposite direction. And then if he pushes down again, it moves back in the other direction. It's completely, I wouldn't say reversible, but you can change the direction.
What material is this?
Zinc.
Zinc.
Right. You would like that.
That's my material.
Yes, I know you would like that one. Okay, so the point is, if you apply a stress, you can move the grain boundary. We've known that since 1953, and people look at it and say, wow, that's really interesting. And life went on. People just sort of filed as the interesting things that we don't understand, and it wasn't until many, many years later that we really understood this. Okay, but that's the old observations. Now, jump forward 53 years, and the group of, this is John Kahn, Yuri Mishin, and Suzuki. And what they're doing is an atomistic simulation. It's a bicrystal. There's the grain boundary. And then what they're going to do is they're going to take the bottom and top surfaces and translate them relative to each other like this. Okay? Some of the atoms we paint pink or red, and the experimentalists used to call this a scratch. It's a fiducial mark, but it's you just color them in the experiment, in the simulations. And let's just watch this. So you're shearing the top to the right. The grain boundaries moving down as the crystal shears over. And what you end up with, if you look at your scratch forms a constant slope here. That constant slope is the ratio of how fast it is this way to how fast the two crystals slide relative to each other that way. Which is to say, the slope is just the normal velocity divided by the parallel velocity. Okay? And so people talk about the shear coupling factor beta, which is the inverse of that slope. Okay, now, in these simulations, they looked at 10 or so boundaries. And the first thing is, if you look at all those boundaries here, the sigma 41, 25, 37, blah, 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 at zero temperature, at low temperature, these are all certain constants. What are the constants? They're just the Berger's vector, the disconnection, divided by the disconnection. It's completely determined by this B over H ratio. Now, the interesting thing happens as you go to higher temperature. All of these inverse betas, they all go to zero. So no longer does this work. So we'll have to understand that too. And at high temperature, if I shear this crystal this way at a fixed rate, when the temperature is very high, the grain boundary just slides. So it just, just literally just slides like it was greased. And there's no translation, but it still slides. Okay, this is grain boundary slide. Okay, so we have to understand how it goes from this beautiful, predictable B over H values to things all drop to zero. All grain boundaries will have beta go to zero at high temperature, except inconveniently some materials melt before it happens. Right? So depending, some boundaries will slide at high temperatures, some will not, and it's just because you can't get the temperature high enough. So not all boundaries slide at the same temperature. This boundary is sliding here at 1,000, and this one at 1,300 is not sliding at all. Okay? Well, why is that? I'm glad you asked. Okay. So, coming back here, clearly the fact that beta is different for different grain boundaries tells you there's a crystallography dependence. The fact that there's a temperature dependence tells you that the energies to form disconnections are different for different grain boundaries. Okay, so that's what we'll go back to. So, remember, for different grain boundaries, you have a different energy spectrum. Okay, here's the energy spectrum. And I can say, well, let me just call for now small q. You'll see why I picked that in a minute. and say that energy, that formation energy, goes like something proportional to the Burgers vector squared, looks like that. Another term that's proportional to the step height. There's the applied stress, the mechanical work term. Oops, that should be a minus sign. And that's the jump in chemical potential part. Okay, like before. The other constants, let's not worry too much about it for now. So if I know the energy to form the disconnections, then the probability of forming one is just proportional to e to the minus energy over kT divided by the sum of all possible disconnections, which we should call the partition function. Okay, so it's that ratio here. That's the probability. If we're going to do kinetics, we want to say what's the probability per unit time. So I need to put in a rate there, but for now, let me not worry about it. So now, remember beta we said was just B over H. But it's B over H times the probability that you have Burgers vector I. This is the probability you have that Burgers vector. And this is the probability you have that step height. So it has those Q's in there, where that Q is just related to this one. But what I've done is I've taken out the driving force terms, and I put it here. And if I linearize this, I just say that the beta just goes like the sum of the B over H's, but you then have a term which is proportional to the applied stress or proportional to chemical potential jump in both those cases. So this is the sum with a B here, sum with the H here. So if I now go back and plug in this spectrum, and I tell you which B and H corresponds to each one, I should be able to not just predict beta, but I should be able to predict beta as a function of temperature. Right? That's what Professor Young was asking me for. What's the temperature dependence, okay? So since different grain boundaries have different energy, formation energy spectra, they have different beta as a function of temperature. So now if I do this, I go back to the cases where they did all those molecular dynamic simulations. I repeat it. These are for five of the same boundaries. They're not exactly the same calculation. Strain control, this is stress control case. But the point is, if I look at sigma 5, it goes to 0 very early. I don't put a temperature scale here, because the absolute value is arbitrary in the model. But if I look at them, first the blue one goes, then this cyan one goes, the green one starts to go at the end, the red one's completely flat, and this magenta one is almost flat, right? The point is, I can predict at what temperature any grain boundary should slide, okay? Because it just comes from the disconnections and the energy spectra of those disconnections, okay? A caveat, because somebody will ask me, well, what happens if there's segregation? I'd say, you have to wait for the next tutorial for that part. Sorry, that was a hint, say, don't ask me. Okay. Okay, so I think it's going to be a little bit long today. I apologize. If anybody needs to leave, don't hesitate. Okay, so if I look at this expression that I have here, you notice that the coefficient of the stress depends on which Burgers vector it is. The coefficient of the step height, of the chemical potential jump, depends on what the step height is. So if I take the same grain boundary, in one case drive it with the stress, and the other case drive it, say, with curvature or a chemical potential jump, I will end up with different values of beta. Okay? So in that sense, shear coupling factor is not really a property of a grain boundary because it depends on how I drive it. But it's completely understandable. It's very predictable, but the point is, this is molecular dynamics data, and the curves are the theoretical part. Okay? Okay. Question?
Just one question about the beta factor.
Yes.
You go back to the slides, you show your two parabolic sine and parabolic sine. So you consider both thermodynamics and kinetics, right? The previous slide. The first one, yeah, right there.
Yes.
The expression for beta, you have a parabolic sine there.
Yeah, right.
That come from the kinetics, not the thermodynamics anymore.
Yeah, so this part is, this is thermodynamics, this is mechanical work. So this has to do with the energy. So it was e to the minus this whole thing, but I took these parts out and I put it in front because remember, e to the minus something plus something else is e to the minus this times minus that, right? So if I do all of that, this is what I end up with. So I just separated them into two terms. And then I just assume that this part is small compared to this, and I linearize it.
Yeah, but you have the minus sign there, so
The minus sign just depends on how I define the sign of h. Sorry, being consistent is really hard. I apologize for that. But that's the idea. Okay. So I just want to mention very quickly, if you take a grain boundary that's inclined to an arbitrary angle like that, call that theta 0, I can imagine that this is made up of a faceted grain boundary of this symmetric boundary and that symmetric boundary. And if I know beta for this one and beta for that one, then I can combine them like this, where theta 0 and theta s are defined here. I can combine them like this. I mean, it just comes out from the geometry. And if I look at that, this is beta versus inclination. The red curves are the simulations. The red curves are this expression here. These cyan and blue data points are the simulations with molecular dynamics and phase field crystal in this other paper somebody else did. And the point is, this simple analytical formula captures all of it. It's not to say that the boundary is really, really faceted. It's just to say if I want to predict the beta value, I can assume it's faceted, and it's the approximation, and it turns out to be not a bad one. Okay? And by the way, this is analytical. I can calculate all these curves in a microsecond, as opposed to the simulation, which at the time took months. Okay? Okay. So up to now, we've been talking about, when we're talking about the finite temperature behavior, I was talking about the beta values as a function of temperature. Now, let's talk about grain boundary mobility. And just to remind you, the grain boundary mobility is usually defined as the ratio of the velocity of the boundary to the driving force. So it's the coefficient that relates those two things. And you always want to do it in the limit that the driving force is 0. Now, in all our textbooks, that is to say, we teach sophomores that the mobility should go like a constant e to the minus q over kt, and it's Arrhenius. Well, we're not sophomores anymore. I always tell students that I'm going to lie to you. The reason I'm going to lie is we have certain simplifications. We say, that's all we tell you. But it's rarely really true. The truth is too complicated. So Liz Holm and her postdoc and Steve Foyles looked at 388 different grain boundaries and made a catalog of the mobilities of all of them. And for example, this is one boundary. They picked out an asymmetric sigma 9 boundary and plot log mobility versus 1 over t. And you get, decent lines. Not perfect, but decent lines. Okay? And the point I want to make here is this is Arrhenius. But if you look at another boundary, this is an incoherent sigma 3. Here I'm plotting log mobility versus log temperature. The slope is -1, which tells me that the mobility decreases with increasing temperature, like 1 over t. And there's 100 boundaries that do this. Well, I don't know if it's 100, but there are many boundaries that do this. This is not exceptional. So it's not like we tell sophomores. And if you go back, I'm not going to go through all this. You go back and look at 388 different grain boundaries and look at the temperature dependence of the mobility. You have cases where it goes up with temperature, cases where it goes down with temperature. You have cases where it goes up with temperature and then down with temperature. You have cases where it doesn't move at all and all of a sudden goes up fast. What is going on here? Okay. It's not like we tell our students. Well, so I will just give you a very quick picture of this. So this is some data from some kinetic Monte Carlo calculations. And this is looking at mobility, in this case, versus temperature. Okay, sorry, I'm a little confused on the notation here. I may have messed that up. The point is, some cases on one boundary, you get this Arrhenius part. And some case, at some temperature range, you get this 1 over T part. Okay? And what's going on here? And this is with one kind of disconnection. By the way, so this is the simulation in black. The blue is the analytical prediction. It's actually something really interesting. Now, in one temperature range, boundary, the way it moves is it has to thermally nucleate disconnections, and you have this thermal activation. Okay? You have this thermal activation. Sorry, it's a long lecture today. I apologize. You have the thermal activated motion. That's sort of the normal stuff. At high temperature, you have thermal activation, but you have so much motion that the boundary is basically random walking. So if I look at the position of the boundary, if I don't put any driving force on, it's just going to random walk up and down, because I nucleate one type of disconnection pair and then the opposite sign. So it just fluctuates. Now, if you put on a large enough driving force, you can beat that fluctuation. You can make it go in a certain direction. You can make it go in a certain way. But if the fluctuations are really large, then the higher the temperature is, you just have more and more and more and more fluctuations, and it's the entropy that's the important part. And the other way of saying it, it's the prefactor in these forms. So you can get both kinds of behavior, and so if I have just one kind of disconnection mode, I can get a peak. If I have two kinds of disconnection modes, I will have two peaks. And so I can have behavior where the mobility goes down with increasing temperature, goes up with increasing temperature, may go up, down, or if I don't have enough resolution, you just say it's independent of temperature. All these things we observe in the large-scale molecular dynamics calculations. Okay, I'll make one more point, and then I'm going to stop, and I will actually do this last part of the talk in the next one. I might have to do a fifth lecture. Okay, this is actually a very small point, but I think it's an important one to realize. Look, when you drive a grain boundary, I can drive it by applying a shear stress. But I can put a shear stress this way on the boundary or this way on the boundary, right? Now the boundary is not the same in the two directions. So imagine this is the tilt axis. So if I do it parallel, shear parallel to the tilt axis, or in the opposite direction, perpendicular to the tilt axis, the behavior should be different. So I can have two kinds of shears because in a plane there are two shears, right? I can also say, for example, have a chemical potential jump across the boundary wants to drive the boundary to migrate. So I can have three kinds of forces. But I can also have three kinds of motion because when I put a shear stress like this, the grain boundary can shear this way. It actually moves that way. Or if it's shear coupled, it can move up. Or if I sheared the other way, if I put on shear stress this way, the boundary can shear like that, or it can move up. Or the boundary can just migrate without shearing. So the point is, I've got three kinds of driving forces and three kinds of displacements. So therefore, the grain boundary velocity is a vector. The force is a vector, so it must be related by a second-rank tensor. So the mobility is not a constant, it's a tensor. Right? It just comes out of the crystal, it just comes out of the geometry of nature. And it's a rank 2 tensor, it's 3 by 3, like that. Now I can go in and actually do molecular dynamics calculation and measure every one of those parameters. So that's a lot of parameters, but there's should be 6 of them, 6 independent ones. And the reason there's 6 is the first thing you notice is that that tensor is symmetric, which is to say if I put on a shear like this and it migrates up, or I put on a chemical potential like this, it'll shear that way. And those two things are the same. That comes out of the Onsager theorem, which just comes out of the entropy production in a Lagrangian system. Sorry if a technical term. But the point is, this term here corresponds to normal grain boundary migration. And in this case, for this particular grain boundary, it decreases with increasing temperature. On the other hand, if I look at shear coupling and I apply a shear parallel to the tilt axis, then the grain boundary starts to move at high temperature, and so that gets faster as you go to higher temperature. And so I've got 6 possibilities. I got pure migration. I have pure shear stress driving a shear displacement. And then I also have all the shear coupling. And the terms here, let's see. So that's a shear in this direction and the motion in that direction. Where's the one I was looking for? Oh, this is shear-shear coupling, which is interesting. That means I put on a shear stress this way, and the bicrystal shears that way. Why not? Right? But the point is, some go up with temperature, some go down with temperature. These tends to be the largest magnitudes, the migration ones. The other ones are much smaller. You can see this and this are an order of magnitude smaller than these, and these are an order of magnitude smaller than those. Okay? Okay, so my plan was today to go ahead and start telling you about what happens when I go into a polycrystal and I start looking at the effects of mechanical constraint on the motion of grain boundaries. So next time, I'll finish that up next time, and I'll do that part. Sorry, I could probably go for another 20 minutes, and I don't want to impose on all of you. But the point is, if you have constraint on the grain boundary, so for example, if a grain is sitting in the middle of a polycrystal, try not to knock that over. If a grain's sitting in a polycrystal, I can't just shear it forever because I have all the other grains around it. So those other grains around it provide constraint. Or if I have a grain boundary and a certain grain size is this big and I shear it, what happens at the triple junctions? It turns out those are all very important effects. And nature is very, very clever in how it handles constraint. And so I'll talk about that, and I'll talk about how to connect this to overall grain boundary motion in a polycrystal. I'll talk about how grain boundaries interact with plasticity at the end in a very short way. And then I'll probably call it quits. If I have time, and maybe I'll do it, maybe I won't, I can talk about dynamic phase transitions of grain boundary, these topological phase transitions with Srolovitz type phase transitions. So if I have time, I'll talk about that, but I'm not sure I'm going to get it there unless you let me do a 3-hour lecture next time. And I don't want to impose. So thank you for your attention, and I'll see the rest of you next week. Thank you. So slide 33 out of 43. Sorry.
Okay, it's a time for Q&A section. And any question?
I just asked a quick question on this slide.
Oh, yes.
So the normal annihilus mode is like the first one, right?
Yeah, that means
So-
you put in like a curvature type
Right.
driving force, and then it's the motion, and
Yeah.
you know.
So in like real polycrystalline materials, but we have so many different kind of mode they can move. And so
Yes.
considering that the first one has much higher order than others, so can we say overall effect is still more like follow the?
Well, yes and no, but if you look at some effects, for example, if you trying to understand why does stress drive the grain boundary, you know, like some of the experiments I showed you, that won't tell you anything about that, right? So it may be the largest, but you know, I mean, reality is this is 0.8, that's 2 point, it's a factor of 3 bigger. The other point is that because of the constraint, often you get the grain boundary to migrate, but when it migrates, it will generate stress. That stress can become large enough that it stops the migration. And unless you know all these pieces, you don't know how to put it all together. I'll show you that next time.
Okay.
It's actually, all these things individually are important, but sometimes some of these effects are only become important when you manage to turn the other ones off.
Yeah.
Or you put on, for example, stress driving force instead of, say, like a curvature driving force.
Okay.
Right? In general, I mean, here, I'll give you a really simple example of where you see this all the time. If you look at a grain in a polycrystal and you do grain growth, right? Then the grain boundary should move towards their center of curvature. But if you actually look at crystallographic texture, it changes during grain growth. And if you watch any individual grain, many grains rotate while the grain boundaries move. All of that is because of this shear coupling. And so, yeah, this may be the biggest terms, but there's certain kinds of phenomena that you can only understand when you include the richness of how grain boundaries really move, not the sophomore version.
Okay. Thank you.
Right? Hope there's no sophomores here.
Dave, I was doing a lot of superplasticity work.
Yes.
Where the grain boundary slidings partitioned the highest contribution to the superplastic strain. So at that time, we usually sort of use EBSD to construct the probability as function of the misorientation angle
Yes.
to get the probability for different sigma 3, sigma 5, 7, okay. So we also try to find what kind of grain boundary would be best for grain boundary sliding
Yes.
at different temperatures. So that can be sort of the support the idea what's the best superplastic strain rate, strain at different temperatures.
Yes.
But today I suddenly confused. Even for a same sigma grain boundary, it could be positive or negative as function of the temperatures.
Right.
So, what's your comment?
So next time, so I will only talk a little bit about plasticity next time, just a little bit. But what I'll try to show you is what's really going on during grain boundary migration in a polycrystal. Because I can go back and dissect what's happening in terms of all of these things, but there's many phenomena that are actually happening there that I wouldn't expect without these ideas. So for example, the one I just mentioned before, the fact that understanding how grains rotate and how you can get the competition between rotation and motion. Because all these things are coupled, because if you go in and try to look at any individual grain boundary, you really can't say much of anything because it's going to depend on what the constraint is. And the constraint depends on what the grain boundaries around it are doing. Because the whole thing has to be is an interconnected microstructure. So I think a lot of the ideas here that I'm talking about are going to be more useful for understanding the phenomena that you see. But if you try to actually make quantitative predictions, you're always going to run into trouble because, you know, there's 5 degrees of freedom associated with every grain boundary. Every grain boundary also has a range of possible disconnections. The dimensionality of the problem is very large, but at least we can use it to understand the phenomena and some of the trends. But to make really quantitative predictions, not so optimistic. I will try to show you at the end next time, well, maybe in the middle next time. I'll try to also show you, you know, normally we say the velocity of a grain boundary is proportional to its mean curvature. And we just put a constant in the front of that. That's obviously not a good expression. It may be true on very much on an average sense, but I'll try to show you what's better than that, even if it's not perfect. But at least it's better. So, yeah, if you really want to predict exactly how any given microstructure and any given material is going to evolve, I'd love to do it. I've written lots of simulations to do this, but you can't depend on it because I don't know what the parameters are, and getting the parameters is the hard part because the dimensionality is so large. So, sorry, it's kind of a grim picture there.
It's a very inspiring talk. And I still want to go back to the statistical mechanics part about, you know, the spectrum things,
Yes.
landscape, because that determines the property and the attributes of the grain boundaries you talked about.
Well, it determines the properties of it's important for the disconnections, and then given that, I can then try to deduce the properties of the grain boundary.
Time dependence of the grain boundary, right?
Yeah.
But that's now, but you don't bring the issue of the chemical complexity into the discussion of the grain boundary.
The what?
The issue of chemical complexity, like, you know, hydrogen things.
Yes.
But if you look at these landscapes, one might suspect that if you add more elements into the structures, you can further enrich the spectrum that involves the grain boundary motion. So in this,
So he's the glass half full guy instead of the half empty picture that I was telling you about. It's a complexity instead of enriched complexity instead of a sad ending. Like I was like.
So
but go ahead. Yeah.
If that's the case, can we say that is that possible you can design the grain boundary by increasing the chemical complexity such that the entropy, you can easily get the entropy dominance region, and the grain boundary becomes very, you know, reluctant to move, so you can preserve the property of materials to a level that the simple metals cannot do that. I want to see a comment on this.
Very interesting question. I mean, I'll start by saying I don't know, but now having said that, I'll speculate.
Right. I think it's just a speculation based on along the line of thinking you just presented. People will naturally think that way, right? There's another dimension you didn't talk about, bringing into your discussion of the grain boundary.
Yeah. I mean, as I mentioned before, I'm trying to avoid all the chemical part for now. But it's an interesting question. So you're saying that if I'm in a system where, For example, the energy landscape. Instead of having this nice landscape like that, imagine I add randomness to that landscape.
Right.
What does that do? So that's sort of
Yeah, that's what
one way of thinking about the question.
But your framework remains the same.
The
will remain-
framework remains the same.
You still have this chemical potential difference. You still have everything, but the landscape become more complicated. So
Yeah, absolutely. I mean, you know, one of the things that we think about is, remember I was drawing, let me see if I can find this very quick. Right? Go back to this picture. Now what we do is we just add a random variable. So this one's very small, this one's 10 times higher, this one's lower. And say now I'm trying to move through that landscape. It's an interesting statistical question, so what the average motion is in that complex landscape. I don't know how to do it. I mean, it's related to some things we looked at. We're just looking at dislocation motion and random alloys. But, so, I don't know.
Okay.
It's a really good question. I don't have a good answer. Sorry.
Any question more?
I think I've kept everybody a long time today. I apologize. So.
Professor, I have a small question about the grand boundary movement and for the mobility, just like the Professor Huang says about the superplasticity of the polycrystal material.
Yes.
And it's highly dependent on the mobility of the grand boundaries. And the grand boundaries also depend on the slide and also the mobility of the
Yes.
Specific grand boundaries.
Yes.
So, as noticed in the superplastic material, we generally think that the superplasticity is mainly depend on the fractions of the random grand boundaries, also the high-angle random grand boundaries.
Usually random grand boundary just means saying that I can't figure out what it is, right? Look how systematic that is. It's a beautifully simple boundary.
We just
sorry.
think we show that there are many studies on the CSL grand boundaries.
Yes.
But actually, like the EBSD test, we can get some either different kind of random grand boundaries with not the CSA structure of the grand boundaries.
Right.
So, what about the mobility of this type of the grand boundaries?
Right. So let me just go back to this one for a minute. This is, if you were doing an experiment,
Yeah.
you would probably call this a random grain boundary, right? Sigma 941. You wouldn't be able to figure that out, right?
Yeah.
I mean, you could get something, but you're not really going to get something like this because you can't identify it. The difference between a sigma 941 and something which is, say, 0.03 degrees different, which is a sigma 963,241, the difference between those two things is just how close, how periodic these little bumps are. Right? That's the only difference. And now if I go to something which is really sigma infinity, that just means I still have a curve that looks exactly like this one, except I don't know where those bumps are because they're not periodic. So sigma as a measure of the properties of a boundary, it's crazy. I mean, this boundary is just a sigma 5 boundary with these little differences. This is just a sigma 5 boundary, right? Because everything from here to there is sigma 5. And then you go blip, blip. So I think trying to characterize things as random boundary, low sigma boundary, high sigma boundary, that's a description that is not a very valuable description. Even though we've been trained since the 1980s, 40 years ago, to think that way, it's not a good way to go. There are special boundaries. The coherent twin, the coherent sigma 3 boundary, that's very special. Why is it special? It's not special because the unit cell is small, because the sigma 5 is also very small. But the sigma 3 boundary, the coherent sigma 3 boundary, is special because the energy of the boundary is almost zero. That's much more important than the fact that it's got this periodicity versus that periodicity, right? So even a sigma 3, if it's not coherent, it's just a general boundary. So, I'm just saying that kind of description, I think, is overused and has led to a misclassification of materials and boundaries for a long time. Sigma 3 is fine if you say, just tell me the density coherent twin boundaries. That's fine. Or, you say if it's like a sigma 9 or something like that, which is a daughter of a twin, if it's coherent. And then when it comes to talking about superplasticity and things like that, and how do I think about what's going on with the interaction with the plasticity, the grain boundary sliding, coupling to the plasticity in the matrix, it's important to understand that complexity. I'm not going to give you accurate numbers, but what I'll be able to tell you is what's the ideas behind how it works. I think with those ideas, we can do a lot better than this sigma classification. It's just the wrong way to go. So I don't mean to give you a hard time. It's the whole community.
Thank you.
If your advisor is here, I'll give him a hard time instead for telling you, for having told you that. Okay. Okay, thank you. So I'll see you all next week.
Okay.
Okay.
Thank you.